The way you store a rotation, a position, and a scale is internally in the engine, and even in rendering and in almost every single aspect of game development, you use matrices to store that data. So let's see, well, what is the structure of a matrix? Usually it's stored in a 4x4 matrix. It's got 4 rows and 4 columns. This can be used to store all of this data that we just talked about. Quite often, we use quaternions for your rotations and vector 3s for your position. In this case, it works slightly differently. So, we have talked quite a lot about basis vectors, right? Where you have some x-axis, y-axis, and you have some z-axis, right? The way rotations generally are stored in matrices is that instead of saving a quaternion, it saves the direction of each of these axes. If you can imagine these 3, that's the direction of the x-axis. So if we want to make an x-axis direction, we could do 1, 0, 0. So now this one is pointing in the x-axis direction, right? These are sort of XYZ components for this vector. So if we rotate this one, if we rotate this whole thing in that direction so that x is pointing in this way instead, then it would be 0, 1, 0 for the x-axis of that component, right? So if you want to do something called the identity matrix, or like a transformation that doesn't do anything, then you would have an identity matrix where the x-axis is 1, 0, 0. The y-axis is 0, 1, because this is the pointing up, right? And the z-axis would be 0, 0, 1. So this whole thing completely describes the orientation of the object. Because what we're getting is that we have every single axis is now fully described as a direction vector. Isn't that neat? That you can store that like that. The next thing is the position of this whole thing. If you have a world space coordinate, if you want this position, then that's the vector going from the world center to the origin of this object, right? That would be this vector. So that vector in and of itself is usually stored as a column in the last part here. This is the x component, which would be, all of these would be 0 in case it's an identity matrix, right? But crucially, we need to remember that this whole section is the position. I think quite often game engines cut off this last part. They skip this row. So you can use this whole chunk here is the rotation, right? But we don't have a scale. You can bake scale into the axes. So for instance, if you replace this one with a 2, then any transformation you're going to do with this matrix is going to be scaled on the x-axis. And then these are probably left at 0. The really cool thing about using this type of matrix is that you can multiply matrices together, and what you're going to get is a combined transformation of one space into another space. And that is really, really powerful. So these types of matrices are used absolutely everywhere, especially if you're doing rendering. Anytime you render a mesh, then that mesh has a matrix for how it transforms into world space. So that would be, a local to world transformation. In rendering, you have the view matrix, the projection matrix, the model matrix, all of that stuff, right? I mean, you can use these to convert between different spaces. This is sort of what a transform does, right? The transform component is sort of the component-based or game object version of a transformation matrix, which is probably why it's called a transform. If you're going to transform a vector versus transform a position, then you need to be careful how you do multiplications with these. So one thing you can do with this matrix, for instance, if you have the matrix of an object, you can multiply a position vector with this matrix, and that will transform that vector from local space to world space. And that's sort of one of the more powerful things about these matrices, that I'm going to say simple multiplication, but it's more complicated than just a simple multiplication. But if you multiply a matrix with a vector, you are transforming that vector into the space that the matrix describes. If you have a vector and you want to multiply a matrix with that, if you're doing this in shaders, this comes up a lot, where you have a matrix describing some transformation, and then you want to multiply your vector with that. So you want a vector that is transformed by this matrix from some local space to world space, say. If you pass in a vector that is 0, 1, 0, let's say this is the vector you want to multiply by. If you multiply that by a matrix in shaders, it's going to set the last component. It's going to get swizzled out to a float 4, so 4 component value. It's going to set this to 0 by default, which means that the multiplication math works out in such a way that this is going to transform a vector, not a position. So this one is actually going to ignore these 3 lines, because this one is 0, so all of these are just going to get cancelled out, and they don't, like, they're going to get ignored and multiplied by 0, right? So whatever position the transformation was describing, it's not going to get used in the final transformation. So if you want to transform a position rather than a vector, then you would need to manually set the last component to 1. So quite often, if you're looking at like shader code or something, you quite often see that people make a float 4 out of their position. You know, this would be the W component of X, Y, Z, and W. So if you're doing shader coding or anything, W is one of those like scary letters that you need to handle correctly. It also comes up a lot when you're dealing with clip space and projections. Yeah, it's a scary letter, but keep it in mind. What about the last line? My matrix math is not that great. I think the last line is mostly there to make the vector math work with float 4s. You can do a lot of matrix math using skipping the last line, but then you can't do like a pure mathematical linear transformation. Last line is skewing. I don't think it is skewing because you can skew using these, right? If you skew the basis vectors, if you set the y-axis to this one, you've skewed it. The operation of multiplying 2 matrices together means that you have some description of the space, right? It's a position and an orientation and whatnot. But if you have another matrix and you multiply these together, it's going to be like you're transforming by one space and then by another space. So you could sort of think of this as hierarchies. Like this could be a child object, and this could be the parent object. Multiplying these 2 together would give you the full description of transforming the child object into world space, right? Because this one is describing a transformation from local to world. This one is describing the transformation from local to parent. But if we multiply these together, you would get the combined operation of child object to world. That's what we need to do.